Hello, everybody. I'm Emily San Martin. I work for CAWST, the Center for Affordable Water and Sanitation Technologies. And today I welcome you to the session on Biochar Adsorbent. So before we start, I just want to give you a little bit of details about the logistic of the program. As you have probably noticed, you're all muted, and we're going to keep it that way for the entire session. This is just because by experience with so many people from different countries, it's a bit hard to manage having people unmuted. So if you want to ask questions, have any comments, please use the chat box that's situated at the bottom of your window, and we can respond, we can answer your questions. So Josh Kearns is going to be presenting today, and during his presentation, we won't interrupt him with questions, but if you have any, feel free to ask them in the chat box, and I will be asking them on your behalf at the end of the presentation. Also, the presentation is being recorded, and you will all receive a link to download the recording sometime next week. Finally, so CAWST is hosting this series of online sessions this week, but we just aren't responsible for the content that's being presented, knowing that those presentations are done by external participants. So as much as we encourage those presentations, we just aren't responsible for the content. I was supposed to say that. So I'm going to unmute Josh, so that we can see. And what we're going to do is just quickly share our webcams with you to just say a brief hello. Just taking some time. Josh, are you here? Good morning, everybody, or good afternoon, depending on where you are. Just waiting for Josh to join us. We're seeing your screen, Josh, but we can't hear you. Sorry about the logistic. Sorry, everybody. It's just gonna. Oh, hi, Josh.
Hey, can you hear me?
Yes, we can hear you.
You can hear. Okay, good. I have to use a plug-in microphone because the microphone doesn't work on my computer.
Oh, okay.
Yeah.
So would you like to share your screen from now on?
Yeah, let's go ahead and do that.
Hi, we can see you.
Do you want me to go ahead and start, or do you have more introduction to do?
I just had a very quick introduction I can do about you. So Josh is an assistant professor in the in the environmental engineering department at NC State University and a member of the NCSU Global WASH faculty. And I guess you've done a lot of research on water and sanitation and application of waste, biomaterials, and absorption processes for control of different hazardous substances. So, yeah, so if you would like to share your presentation, maybe stop your webcam and share your presentation. I'll also mute myself so that you don't have any background noise while you present.
Okay, can you see my slide now, my title slide?
Not yet.
Okay, let me see. Not showing anything. My screen. How
yes,
about that?
we can see your screen now.
Okay, cool. Let me see. It keeps swooping back and forth. Okay, so do you just see the slide? Is that what you see?
Yes.
Cool. All right.
Okay.
I'll go ahead and get started then. Cool. So yeah, I'm at NC State University in Raleigh, North Carolina. just started as an assistant professor in our new global water and sanitation cluster that we're putting together now. And I'm going to talk about basically a reduction of some of the work that I was doing during my thesis at University of Colorado on adsorption using biochar, essentially as a surrogate for activated carbon, the way that we use activated carbon for controlling trace chemical pollutants in drinking water. And I developed a method for making biochar in the field, which I'll talk a little bit about, so that it can be effectively used in water treatment to target specifically organic chemical contaminants. For an introduction to the talk, I'm going to start out by providing a little bit of context. I've learned over the years that I have to do this a lot of times when I'm giving presentations or seminars to people that deal with water and sanitation or WASH development, because it's sort of a strange thing from my perspective as an environmental chemist, that in the WASH sector has really not appreciated the role of chemical contaminants in drinking water in the developing world. To the extent that water quality is addressed, it's usually addressed in the context of pathogens, fecal microbes and things like that cause diarrhea. And obviously it's a very important problem because a lot of people are getting sick, especially children getting sick and dying because of waterborne diseases that are caused by microbial contaminants. But this whole issue of chemical contaminants mostly has gone ignored by the water and sanitation development community, with the exception of some regionally specific chemical contaminants like fluoride and arsenic, and things like that. So whenever chemical contaminants are discussed, usually people mean fluoride and arsenic in certain locations. And those are obviously very important problems as well. But when it comes to organic chemicals, this is something that just hasn't been appreciated or dealt with yet, but it's a big gaping hole in safe water programming. So we're trying to fill that with our work focusing on chemical contaminants. And I'll talk some about the classes of things that I'm referring to. So we'll give a little context and background on that challenge in WASH, and then talk a bit about adsorption processes and biochar as a low-cost surrogate basically for activated carbon for control of chemical pollutants, and how biochar can be integrated with other treatment steps to address also microbial contaminants and other water quality parameters. So that might be interesting for the audience of CAWST, because CAWST has done a lot of work on biological sand filtration. And we use a version of a biologically active sand filter as part of our base treatment system, combined with biochar for water treatment. That's what's shown in this little cartoon on this slide here. Most of the stuff that I'm going to be referring to is this kind of basic treatment train, where it starts on the left. We have a gravel roughing filter that removes turbidity, particulates, things like that. Then a biologically active sand filter that removes particulates, biodegradable compounds, pathogens, and things like that. And then finally a biochar adsorption step to remove dissolved chemical contaminants, and then a clean water storage tank. So that's our sort of base model system, and I'm mostly going to be focusing on the biochar component of that for this talk. So here are a couple of photographs of the systems that we have worked on. These were developed in collaboration with rural communities in Southeast Asia, hill tribe communities, and farming communities. We've come up with several different designs, but the two most popular ones are we call the blue barrel design, pictured here on the left. Produces about 300 liters per day. On the right, there's a larger concrete tank system that can produce about 2,000 liters per day. And these systems are all made with local materials, locally available materials and supplies, local labor. People are familiar with these materials. They have all the hand tools and things that they need to work with these materials. So they can be done actually at very low cost using all local labor and materials. People can maintain them essentially in perpetuity. The system on the left, the blue barrel system, was designed along with hill tribe people who live a relatively insecure existence. They're often having to leave where they're staying because of political instability or some other problem like that. And they wanted a system that they could basically disconnect it, dump out the media, transport the barrels and the plumbing to a new location where they need to set up for a while, gather all the media, generate the biochar on site, and basically have a system that was semi-portable given their kind of insecure life. So that's the system that we came up with them. In Thailand, where people are a little more settled, they can build a little more infrastructure. They have access to concrete and things like that. So we came up with a bigger system. But these have been quite successful and have kind of gone viral. And so there are hundreds and hundreds of them out there in the world now. I don't know the total number of systems that have been built. We have open access materials online at the Aqueous Solutions website. It's AQ Solutions, one word, aqsolutions.org. So you can go on there and download manuals for how to construct these, and people from all over the world take our materials and go out there and build systems. So that's been an interesting challenge. How do we keep up with all the activity that's been going on? But anyway, I wanted to highlight that, especially in Southeast Asia, the systems have really taken off for the rural people that need to be pretty self-reliant in managing their livelihood. And there's this pretty humorous short video made in Thai language with English subtitles that's been viewed many, many thousands of times, that describes the functioning of the concrete tank system. So I encourage everybody to go check that out. It's pretty funny. You can get the jokes even if you don't speak Thai. So anyway, and when we published the most recent version of the manual for how to construct this and posted about it on Facebook, within a couple days, 25,000 or so people were reached and downloaded the manual. Not because of really our reach, but because this community-based local self-reliance organization that promotes our work is really popular in Thailand. So they have a big social media following, and so that kind of caused everything to go viral there for a little while. Anyway, the challenge that I want to stress to people that are concerned with water and sanitation development, it seems pretty straightforward, but it's basically to provide water that's biologically and chemically safe. And you have to do it under pretty severe resource and economic constraints a lot of times in the developing world. And so really so far the people that have been in the WASH development sector, to the extent they focused on water quality, it's all been microbiological. This week here in North Carolina is the UNC Water and Health Conference, which is big, probably the most important conference in the world that happens every year for water and sanitation development stuff. And I have their abstract books from this year and going back for several years. And there's basically no mention of chemical contaminants by any of the talks, any of the presentations of posters. The only time that chemical contaminants are brought up at that conference is when it's done by my collaborators, me or people that I work with going to talk about it. So it's true again this year, there are no presentations on chemical contaminants in water at that conference, which is really disappointing. It's a major hole in safe water programming. So what kind of chemicals am I talking about? Agrochemical runoff, pesticides, pharmaceutical residues. A lot of pharmaceutical manufacture is done now throughout the developing world, in China and India and other places like that, because it's cheaper, because they don't have environmental standards. So they're some of the highest levels of pharmaceutical residues that have ever been detected in environmental waters have been in Asian countries. Various industrial effluents, waste breakdown products. There's a big issue with breakdown of e-waste whenever we send our old computers and phones overseas to be dumped and recycled by local people. These are basically giant toxic waste sites that are leaching heavy metals and other organic contaminants into the surrounding ecosystems and affecting the people who work there and live near there and affecting the water sources. So that's a big problem. So these are the kind of chemicals that we're mostly focused on. And like I said, this has been a neglected issue in WASH programming. And so we need affordable and accessible technologies that people can manage for themselves in these environments where they're getting little or no support from governments, little or no support from the global economy, but they're basically going to have to be self-reliant in protecting themselves from these environmental harms. So as I mentioned, there's a lot of untreated chemical effluent going in directly into the surroundings around factory zones in China and India, Africa, and other places. Some of the highest levels of pharmaceuticals are detected in environmental waters, for example, in India. In this river that's pictured here in the top right, if you drink a liter of water from that river, you get more than a daily adult therapeutic dose of Cipro. because this water is directly receiving wastewater from antibiotic manufacture. So it's a huge problem, and if you think about the threat of antibiotic resistant germs developing in the environment, it's a perfect environment to develop antibiotic resistance with high amounts of this stuff going into the watershed all the time. E-waste, as I mentioned, is a huge environmental hazard and health hazard. And then most of my work, since I've worked in rural areas in Southeast Asia, has focused on agrochemicals as a major source, major public health burden in these kind of places. So I wanted to highlight that just to give you a sense of the extent to which the water sanitation sector has kind of missed the boat on this topic. Several years ago, back in about 2012, I contacted Waterline's journal, which is one of the premier water and sanitation journals for practitioners, and pitched the idea of an article on a research project we had just completed looking at biochar adsorbent for control of herbicide in drinking water. And the editor wrote back to me and said, well, it sounds like an interesting project, but I don't think herbicide is a problem in the developing world. And I was just absolutely shocked. I couldn't believe that someone would think that, but that seems to be the level of understanding most of the time that we're dealing with in the wash sector, unfortunately. And then fast forward to 2017, a famous professor from the UK published this book, Can We Know Better? Reflections on Development. And he uses the sort of framework of blind spots and talks about blind spots a lot, which is a term that I've used, saying, you know, chemical contamination is really a blind spot in safe water programming. And so I got a PDF copy of this book and I went through it, especially the whole chapter on blind spots, and there's no mention of chemical contamination in safe water programming. And so chemical contamination is such a blind spot that it doesn't even make it onto a list of blind spots. So it's a very meta blind spot. So that's a big problem in my opinion. To give some trends of where the problem is now and where it is likely going, we look at some graphs here on the bottom. If we look at the bottom left, this is chemical production measured in billions of dollars from 1970 through 2010 and a projection for 2020. The gray bars are high income countries, US and Western Europe, and the colored bars are low and middle income countries. And so what you can see is that chemical production really has shifted from the developed world to the developing world. And if we plot those data and try to fit the growth rates, we can see a linear growth in chemical production in the developed world, but perhaps an exponential growth in chemical production in the developing world. And this has happened especially since the economic crisis from about 10 years ago. So for reasons of profitability, a lot of companies have moved overseas where labor costs are lower, where environmental protections are lax or non-existent. So to maintain profitability, that's where a lot of chemical production, use, disposal, and pollution is going. And so that's worrisome from an environmental health perspective. And we can look at a couple of case studies. For example, you know, decades ago in the US and Western Europe, we banned organochlorine pesticides because they're very toxic, they're highly environmentally persistent. So things like DDT that you've heard of and other organochlorines have been banned and phased out in the affluent world. But you know, we had huge stockpiles of these chemicals. So what do we do with them? Well, we donated them and classified it as development assistance. And now throughout Africa, there are storehouses of obsolete banned organochlorine pesticides that are just stored in little shacks and ramshackle circumstances where they're being sold on the black market, they're still being used, or they're just sitting there and slowly leaching into the surrounding environment. So there's a huge problem with stockpiling of obsolete agrochemicals in developing countries. It's a real environmental justice issue. And then another contemporary example, a big environmental water contamination issue that's been a hot button issue recently in North Carolina is contamination of our river basins with fluorochemicals, Teflon-like chemicals that are major health problems, have just been dumped into our rivers for decades by companies like DuPont. And there are a couple of legacy perfluorochemicals that about 10 or 15 years ago started to be phased out in the US and Western Europe and high income countries. And their production, you know, didn't go away. It basically just shifted to China and India and other developing countries. So we have a serious problem with chemical pollution throughout the developing world today, and we can expect it to get worse with time rather than better with time, because that's where a lot of chemical use, production, manufacture, disposal, and so on is occurring. So we think that the water and sanitation sector had better wake up to this problem really quick and start to do something about it, because it's absolutely false to make any claims about providing safe water unless you're very certain that the problem of chemical contamination is not an issue in the area where you're working. And it's very difficult to know that kind of thing. So we know that the problem of pathogens is very acute. A lot of children are dying from diarrhea, and we're of course not suggesting that any resources be taken away from addressing pathogens, contaminants in water. But you know, on top of that challenge, we have this also challenge of chemical contaminants, and there are synergies and interactions between these type of water contaminants. So exposure to chemicals can reduce the immune system and exacerbate disease and issues associated with pathogen exposure. Infections incurred at a young age can increase the susceptibility to diseases like cancer and other issues, chronic issues later in life. So we know that biological harms and chemical harms can kind of work in tandem to produce synergistic negative effects. So we really need to be looking at all dimensions of water quality and water safety simultaneously and coming up with ways to deal with those. So I always like to emphasize the sustainable development goals when you're talking to water and sanitation development people, because we always sort of key off of these. And there are several mentions throughout the sustainable development goals for controlling exposures to hazardous chemicals in air, water, and soil. So it's mentioned in there, and there are definitely people that are recognizing that it's a problem. It's just that action on this hasn't really trickled down to the wash sector yet. So we're trying to provide that component. And in order to drive that issue forward, we created this wash toxics interdisciplinary working group, which you can go online and join. And there's not too many emails or anything that get sent out. We just had our annual symposium yesterday here in North Carolina at the International Society of Exposure Sciences conference was here, and they hosted our symposium, and we had a bunch of talks. It was really good, really interesting. And we're going to try to have an event every year. Last year we did it at the UNC Water and Health Conference. Our event was the only time that chemical contaminants were mentioned at the Water and Health Conference. That's partially why we held it there, so at least there would be some people talking about chemicals at the UNC Water and Health Conference. This year we decided to have it at the Exposure Sciences meeting and try to get, you know, exposure sciences people who are very aware of the problem of chemical exposures, but who are mostly working in affluent world context, but to try to get them interested in applications in the developing world, where a lot of times the exposures are much worse than here in the affluent world. So anyway, I'd encourage everybody to go and check out that website. So now we'll talk a little bit about a possible solution to some of these issues, adsorption processes for controlled chemical pollutants. I'll talk about biochar and some of the laboratory and field research that we've done to work on this technology, and how it integrates with other treatment steps for a sort of holistic approach to water quality in the developing world. Basically, the main concept to understand about how adsorption works is, if you have a highly microporous material that has a really high internal surface area, like activated carbon, there's a lot of space inside tiny pores inside the material for trace contaminants to adsorb to. So here I'm showing electron microscope images of a piece of Longan charcoal or Longan biochar, and you can see at this scale of size, these grains are each about 1 millimeter across that are pictured here, and you can see a bunch of macro sized pores in these. And if you go into those pores, you'll find yet smaller pores, and if you go into those pores, you'll find yet smaller pores, all the way down to the nanometer scale. And it's that internal porosity that provides a lot of surface area. In the case of a good water filter biochar, you're talking about, say, 500 square meters per gram of material. So like a tablespoon of material could have 500 square meters, or like the size of a soccer field, something like that, surface area internally. And that's really creating that internal surface area. Microporosity is pretty much the key to getting a good adsorbent material. So, but activated carbon is not something that people could generate locally, because it's done, you know, at the industrial scale using sophisticated processes and reagents and things that people don't have access to. So really the focus of our research is like, okay, well, you can make biochar in your backyard for very cheap, can we optimize that process to make a material that's good for water filtration? And the research started by examining the most widespread extant technology for producing biochar or charcoal, which are traditional style charcoal kilns. I spent a couple years traveling around Southeast Asia studying artisanal charcoal production using these small kilns made from bricks and mud or made from steel drums and then, insulated with earth. The way these systems work is you pack them full of the wood material that you want to make into charcoal. You have another big pile of wood that you burn at the front of the kiln at the firing port, and you use the chimneys to establish draft through the kiln to suck the heat from the fire into the kiln and carbonize the wood that's in there. And the process, in the case of the kiln here on the left, the beehive kiln, it takes about a week to make that into a batch of charcoal. On the right, smaller kiln made from a 200-liter or 55-gallon steel drum inside of the adobe structure. That takes basically firing it all day and letting it cool down overnight to make a batch of charcoal. And these systems are designed to make charcoal for cooking, which is a predominant cooking fuel in a lot of places in Southeast Asia and other places around the world. And they're certainly not optimized for producing a good water filter material. They're not the most environmentally friendly processes around. They produce a lot of smoke and products of incomplete combustion, greenhouse gases, particulates, that sort of thing. From the operator's perspective, they're not super pleasant because you're getting smoke in your face all the time and you have to babysit the kiln and it takes a long time and it's a lot of work. So they're not optimal from a user perspective or an environmental perspective, and they don't produce optimal water filter materials, but they're super widespread. It's familiar just about all over the world. And so it seemed like a good starting place for investigating the capacity of these materials to act as water filters. Most people, at least in my experience, that live sort of traditional rural lives in Asia are at least familiar with the idea of using charcoal in water filters. That idea goes back thousands and thousands of years. So it's really an ancient approach. The question is, can it be done in a way that's effective for a lot of modern chemical water pollutants like pesticides and things like that? Pesticides have only been around for about 100 years. So that's really the question that we're asking. And but in order to try to find a method that's more optimal for making water filter char, as well as more environmentally friendly, and to be able to use a wider variety of biomass feedstocks rather than just going and cutting down trees and making charcoal, we wanted to look at a variety of agricultural and forestry waste materials to make into charcoal. So we adapted a design that was developed by the clean cook stove community for people who have to cook over an open fire indoors. There's a lot of problems associated with respiratory illness and eyes and skin and so on from smoke exposure indoors. So people have tried to come up with cook stoves that burn cleaner and more efficiently. And these little gasifier devices produce a residual char. And we tested that char and found out that, hey, it's actually pretty promising for water treatment. And so we wondered if we could scale that up to a larger scale to make substantial quantities of char that could be used in water treatment. And we came up with this drum oven design that can be constructed out of just a couple of steel drums and scrap metal. You can make all the cuts and things that you need to make the drum with just a machete and a mallet. So you can actually construct these like as shown here in this picture. These were all done with just hand tools, no electricity was needed. They are very low emission systems compared to traditional charcoal kilns. You can see a bit of steam coming out of this drum oven. That's just steam because the hillside man there is quenching the drum oven with water. But when they're operating properly, they don't produce any smoke. They actually burn all the chemicals that would become smoke, and that's what provides the heat that drives the process. So they're more energy efficient in the sense that the material that is being turned into char provides the energy that turns that material into char rather than having a second pile of wood that you have to burn to provide external heat energy to make char. So we've looked at a whole variety of agricultural and bio-waste feedstocks for making char with these devices at the cook stove scale and at the drum oven scale. We find that if they're operated at high temperature, emitting a little bit of oxygen to the process, it kind of burns out the char and opens up the pore structure, providing a lot more internal surface area, makes a material that's more like activated carbon and better for water treatment. So we spent several years kind of optimizing this process, and we have a pretty good design now. And we're working on ways to further optimize it and increase sorption capacity by kind of creating a pseudo activation process that you can do under field conditions. So anyway, tested a lot of chars from these devices, and these devices became really popular again in Thailand. It kind of went viral. Another one of these humorous videos describing the process, which you're welcome to go online and check out. But the thing that most attracted people to it was that it only takes about 2 hours to make a batch of char this way. And because there's no smoke, people are really, really bothered by all the smoke that comes out of the charcoal kilns. It's really unpleasant. And so the Thai people were really excited that you could make a batch of charcoal in 2 hours instead of a full day cycle, and no smoke to bother the operator. So I would say there's just been hundreds, if not thousands, of these little drum kilns built around Thailand now because they're really popular. So anyway, how do we test this char to see if it's any good for water treatment? And considering the plethora of chemicals that are out there and the changing conditions, it's really hard to try to verify these things in the field, although we have some proxy ways of doing that, which I'll get to. But the process that we've used is we started with the actual operational conditions of one of our field biochar treatment units. And here we're looking at the system that produces about 300 liters per day. It has an empty bed contact time of about 8 hours and a bed volume of about 100 liters of char. And we use the operational parameters of the full-scale field biochar treatment system. We plug those parameters into something called the pore and surface diffusion model, which I won't go into detail today, but just to say that these are a bunch of equations that describe mass transport in a filter system. So mass transport meaning you have some mass of chemical pollutant that's in the water. It has to diffuse through the water to the surface of the adsorbent, across the boundary layer at the surface of the adsorbent and into the pores and down through the pores, and then finally react and adhere to the surface of the adsorbent. And so you can describe all that transport mathematically, and if you maintain similarity in those mass transport properties, you can scale the full scale larger system down to a very small laboratory scale system. In this case, for most of the experiments, we used a tiny little column that was only 4 millimeters by 10 millimeters in size, and we could pump various test solutions through that column. We could try lots of different types of char in that small column, and we could basically simulate a year's worth of operation of a full-scale field biochar treatment system in a few hours. And so this allows us to look at lots of different char production conditions and lots of different materials and lots of different solutions and lots of different contaminants and that sort of thing to get a sense of how well this works. And basically with this mathematical model that we use, we can go back and forth. We can look at data that are collected at the small column scale in the laboratory. We can transform those data mathematically to predict how a full-scale real-world biochar treatment system would perform under similar conditions in the field. And this kind of iterative back and forth process between the real-world system and the laboratory system is how we've kind of honed in on a set of design principles that are conservative and give us confidence that the field scale systems are operating hopefully according to plan. And so I'm going to show a few data today if we have time. Let me check the time and make sure I'm not running over. But I want to show a few data from laboratory tests and to give you a sense of the kind of work that we've done. I'll show a bunch of graphs that look like this, where on the y-axis you have normalized concentration. So that's the concentration of the pollutant in question emerging from the column divided by its concentration going into the column. So it scales between 0 and 1. On the x-axis you have a column throughput, which could be in terms of time, in terms of volume of water. In this case, it's normalized. So it's volume of water treated per gram, liter of water treated per gram of adsorbent in the column. So it's normalized. And so basically, when you plot the data this way, you get a breakthrough curve where at the beginning of the column experiment, you have basically no pollutant coming out. It's all being absorbed onto the char. Over time, it starts to break through and come out of the column. And then by the end of the experiment, the concentration of the pollutant coming out of the column is essentially the same as the concentration going in, because the material's totally saturated and it's not taking up any more pollutant. So we call this a breakthrough curve. So I'll show a few breakthrough curves. One of our common test compounds is 2,4-D, which is a very common herbicide. It has some important public health, human health impacts. Also, it's an anion. It's very difficult to absorb. It's very water soluble. So we tend to pick compounds to focus on that are really difficult to absorb using biochar or activated carbon. Because if we can absorb the difficult ones, then we assume that we're doing a good job controlling the ones that are removed much better by adsorption. And then I'm also showing a purple curve here for UVA 254. So this is basically the ultraviolet adsorbance signature of the background solution. This experiment here was done in surface water. The background organic matter component of surface water can absorb UV light at 254 nanometers. And the reason that we track that is because while it's very difficult and expensive and uncertain to try to measure trace contaminants like 2,4-D in the field in Thailand or Burma or wherever, it's easier to measure UV absorbance using a small field spectrometer. So the idea with tracking UV absorbance of the background solution is it could give us potentially a conservative tracer or proxy for the bed life of the char. And so we measure that in the lab along with our experiments measuring pollutants, and we can also measure that in the field and sort of use it as a sort of reality check on how well things are actually working in the field. So here's one example breakthrough curve for the small 300 liter per day system. So what I'm showing here, these dots, these are column data. They're the same column data as shown in the graph at the top left, but I've just changed the axis from a logarithmic axis to a linear axis, and then fit those data using the pore surface diffusion model, that mathematical model I was referring to. And then when I consider the operational parameters of the full-scale system and using that model fit, I can generate a predictive curve, which is the curve to the left where it says full-scale biochar contactor PSD and model prediction. That is what the pore surface diffusion model predicts would be the breakthrough curve for the 300 liter per day blue barrel biochar system. And these units here on this graph are not particularly useful for considering something in the field. So if we just take that predictive curve and we put it onto more useful units like days of operation at a throughput of 300 liters per day, and we consider a high but potentially environmentally relevant concentration of 2,4-D herbicide in surface water of 100 micrograms per liter, what this graph is showing is what the breakthrough curve of 2,4-D at an influent concentration of 100 micrograms per liter might look like in a full-scale system. And with this system, we recommend people to change their char once per year. So what this is suggesting is that at a year of operation, this system would be expected to be removing 2,4-D at about 80 or 85% after 1 year. And that for a high concentration of 2,4-D coming in of 100 micrograms per liter, that would be below this level of 30 micrograms per liter, which is the World Health Organization guideline value. So the World Health Organization says, if you believe them, that it's okay to drink water that contains 30 micrograms per liter or less 2,4-D herbicide. So we chose that as a sort of indicator of like, is our system performing and providing water that maybe people would consider acceptable for consumption. So this is 2,4-D in surface water is one example. And here is, we're looking at several different biochars here made either in the little cook stove scale gasifier or the drum oven scale gasifier from a bunch of different materials. The 2,4-D breakthrough curves are in blue. The UVA breakthrough curves are in purple. And what we saw is that with these high temperature chars, that whenever you reach about 90% UVA breakthrough, then your 2,4-D breakthrough is at about 10% or less, approximately speaking, under these experimental conditions. And we saw that consistently for different scales of biochar production as well as different materials, as long as the temperatures were high. And so that suggests that maybe this UVA measure could be a field measurable proxy to allow us to evaluate the real world performance of our systems. And this is a picture of the longest running biochar system that we installed in a farm community in northern Thailand in February 2008. To date, it's produced I think about 4 million liters of water, saved the community over $60,000 US if they had to purchase their water just for the system. And we did a tracer study looking at UV absorbance from this system. And what we can do is use these breakthrough curves for 2,4-D that were collected in the lab, do that same mathematical transformation that I was talking about to predict what 2,4-D breakthrough would look like in this real world system, and then overlay the field data that were collected. So these are actual field data from the full scale system of UVA adsorbents. You can see there's more scatter in the data because it's in the field or collected over a couple of years. There are rainy seasons in there and changing water quality and changing water sources and all this sort of thing. So a bit more scatter in the data, but we can roughly see that approximately this relationship of UVA breakthrough and 2,4-D breakthrough holds. I don't want to give you the impression that the formula is always 90% UVA breakthrough to 10% 2,4-D breakthrough. It's not that hard and fast, but it's just that, you know, we're looking for field feasible measurements that can give us conservative indicators of how well the systems are performing. And this UVA is one approach that's kind of a work in progress. So it's nice to see like a reasonable degree of field confirmation for something that we developed in the lab. That's mainly the take-home point. Don't get too attached to the specific numbers of 90 and 10. And so to wrap up, I'll show a couple of more examples. Here we've done a similar thing considering the Blue Barrel 300 liter per day system and imagining PFAS, perfluorinated compounds, a couple of well-known perfluorinated compounds, PFOA and PFOS, in groundwater. And so what this is suggesting is that if your goal is to get 90% or better PFAS removal using the 300 liter per day biochar treatment system, that for PFOA, you should recommend changing the char at least every 4 months. So PFOA is very, very difficult to absorb, so it breaks through quickly. We see that also with activated carbon systems. So the point here is that when you're considering how these systems operate, you have to take into account not only the target compound that you're interested in, but also the background water matrix, which has a huge influence on how adsorption takes place. And some compounds adsorb much more strongly than others. For example, PFOS adsorbs much more strongly than PFOA. So there's a lot of factors to think about. And then a final example, sulfamethoxazole is a human and livestock antibiotic, very commonly used, also very difficult to remove by adsorption. And it's commonly found in wastewater effluent. And what this simulation is suggesting is that if your treatment goal is to get 80% or better sulfamethoxazole removal from a wastewater effluent or from a surface water, for example, that's impacted by a wastewater release or a sewage release, this suggests that a 6-month biochar change-out time would be a better choice than, say, a year or longer, because sulfamethoxazole is difficult to remove, and because wastewater organic matter is very effective at fouling adsorbents and reducing their absorption capacity. So again, the take-home point is don't get too attached to 4 months, 6 months in these different compounds, but the challenge here is what kind of pollutants are you facing, in a given area where you're working on a wash development project. Is it an agricultural area where you're more concerned about pesticides? Is it an industrial area where you're concerned about industrial chemicals? Is it, pharmaceutical or what? And what is the quality of the background water? Is it surface water? Is it wastewater? Is it groundwater? And so on. And those all have important effects on the efficacy of the system. And so finally, I think that's probably it, and probably we have some time to take some questions. So I hope you enjoyed the presentation, and please do note my email address and follow up with me if you like. And I look forward to working more with the wash sector to integrate biochar treatment with other steps for controlling pathogens and other water quality parameters. Thanks.
Thank you very much, Josh. That was a very, very interesting presentation. We have a few questions from the participants. So first question from Brian is, can organic contaminants interventions be used to replace household water treatment interventions?
So the question is, if I get this right,
if basically
can this be used at the household level?
I guess that's how I understand the question as well. Yes.
Mm-hmm. Yeah. Yes. So the open source materials that are currently available online on our website basically give you sort of cookie cutter instructions for setting up either of these two systems, the 300 liter per day system or the 2000 liter per day system. We're working on a set of instructions for practitioners that will allow you to adapt those designs to different purposes, different treatment scales, including smaller scales like household, as well as larger scales like larger community. The important thing is to follow a set of design guidelines, like the CAWST people will be very familiar with the design guidelines that are important for biosand filtration, including the depth of the sand, the time that's necessary for developing the biofilm at the top of the sand, and so on. And so the next thing we're going to produce will be for practitioners who don't want to build just exactly the systems that we have come up with, but want to actually use the engineering principles and the science and the research behind all that to adapt to their own designs, including at the household scale. We had published a paper a few years ago in the Journal of Water, Sanitation, and Hygiene for Development that discusses using biochar treatment, for example, as a final polishing step before consumption of household drinking water, because a lot of people in the developing world really object to the taste and odor of chlorine. And chlorine is very important for disinfection, but it tastes bad, it smells bad, and a lot of people hate it and they'll avoid it. And so to encourage safe water practices, the scenario that we envisioned was you add chlorine to water that has a high amount of organic matter, because surface water or something like that. The chlorine kills the pathogens, but the chlorine also reacts with the organic matter in the water to form compounds that have health concerns like carcinogens, things like that. So we looked at, can you remove the harmful compounds that are created when chlorine interacts with organic matter, and can you control the taste and odor of chlorine so that the water is more palatable and acceptable and encouraging people to have more safe water consumption practices. And so, yeah, there are options for adapting this to the household scale. And in fact, a lot of what drives uptake of biochar systems, because a lot of these trace contaminants, they're odorless, they're tasteless, you don't even know they're causing harm. But what makes it the most popular for people mostly are aesthetics. It can make the water appear clearer. It can remove weird tastes and odors. It can remove chlorine and residuals from disinfection and that sort of thing. And the aesthetics, the improved aesthetics of water after it's been treated with biochar has been probably more of a selling point than the trace contaminant control in many locations.
Thank you. And maybe I could add to your answer in terms of household water treatment. What has been studied so far for household water treatment was really based on biological contamination, and more in the communities of intervention, we recognize that chemical contamination is a huge factor, as Josh just explained. So it is for the wash sector to recognize how those technologies like biochar can be adapted to a household water treatment smaller scale. So I mean, we're still learning together how those technologies can be combined as well. So there is another question from me here. Okay. I would like you to explain a bit more about the breakthrough curve. The breakthrough curve you talked about in one of your slides.
Do you have any more information about specifically what?
The question is, can you please explain breakthrough curve in detail?
Breakthrough curve in detail?
Mm-hmm.
All right, well, let's go back and maybe just walk through it again if it's a little confusing. So I'll just use this generic one, and it's just a drawing of a breakthrough curve. Mm-hmm. So the idea is that you're considering a particular contaminant of interest, and it's at a certain concentration. Let's see, let's look at the diagram here. So if you look at this picture, the way we set up these experiments is we have some kind of a vessel containing the test solution, which, for example, could be a wastewater with pharmaceutical residues in it. It could be a surface water with herbicide residues or what have you. We pump the water out of that solution, pump it through a column full of biochar and into a waste receptacle. And so what the breakthrough curve is basically if you look at the concentration of the contaminant of interest in this column effluent over time. At the start of the experiment, all of the contaminant is being absorbed here onto the biochar in the column. And over time, that biochar fills up to where it's not going to be able to take up any more contaminant. And then as that happens, then the concentration of contaminant in the effluent of the column starts to rise. And at some point, the char is basically not doing anything anymore, and you're just pumping the solution through the column, and there's no more room inside the adsorbent for the contaminant to be removed, and so it's just passing through. And so the concentration over here in the effluent will be the same as the concentration in the influent. And so, when you plot that, basically this axis is time, or the volume of water passed through the column, something like that. And this is the concentration of the contaminant that you're concerned about. At first, that column effluent, there's basically nothing coming out. And then over time, the concentration starts to rise, and then by the end of the experiment, the concentration of the pollutant in the column effluent is equivalent to what it is in the influent. Here it's relative, so it's varying between 0 and 1. So hopefully that explains it. The shape of this curve, whether it's a very steep curve or a very relaxed curve, depends a lot on how the experiment is set up, and also how the contaminant gets taken up in the column. So that's an important sort of chemical process parameter that we look at, the shape of this curve, and also when the contaminant starts to break through. The ideal situation is you can run the column for a long time, and it takes a long time for the contaminant to come out. So a better adsorbent would break through further out here. An adsorbent that's not very effective, you would start to see the contaminant come out really early. So we've looked at a lot of chars, and I only showed a handful of ones in the talk today, but many of them will break through long before a lot of the chars that I showed. Hope that helps.
Yeah, I understood. Another question from me here is, can the used biochar be regenerated and reused?
In principle, it could be, but the question is it worth the time and effort to try to regenerate the char and reuse it versus if you're in like a tropical setting, you probably have a lot of biomass on hand. And so if you're replacing the char once a year, once every 6 months, you could go to the trouble of taking the char out and drying it, and then, putting it into some kind of system to heat it and regenerate it, or you could just go and use, by that point you've accumulated some more waste biomass from whatever process is going on nearby, whether it's coconut shells or wood or bamboo or prunings from fruit trees or whatever it is, and you could just make a new batch. So probably because it's a a locally sourced material, a waste material, surplus material of some kind, it might just make more sense just to make new char rather than trying to regenerate the old char.
Right. So a good question after this one from Brian is, how do you dispose of the used char that is full of chemicals?
Yeah. Well, the first thing to remember is that we're dealing most of the time with trace chemical pollutants. So they're in the water at parts per billion or parts per trillion levels, whereas the background organic matter of surface water, for example, is going to be parts per million. So mostly what's in the char is just generic background organic matter with a little bit of trace chemicals. I didn't show the data today, but we've done a lot of studies of desorption. So once we run a column study to the point where the material is saturated with the pollutant of concern, then we shut off the pollutant coming into the column and just run the background water through, and we try to look for the release of that pollutant back into the water. And what we see is that, especially in the presence of organic matter, just background organic matter, you don't see a lot of desorption of the pollutants. So they pretty much diffuse into the pores of the adsorbent, and they're stuck there, and then they're continually piled on by organic matter coming into the system. So we don't see a lot of back diffusion or release of pollutants. But our recommendation, I mean, if you wanted to be quite strict about what to do, you should take the char out, you should dispose of it in a lined pit, and protect it from any sort of groundwater or that sort of thing. In reality, that's probably not going to happen. And so we try to think of what are the best tools that people have at their disposal to deal with the material: time, temperature, and the action of microorganisms. Some of the work by my colleagues in the lab has shown that over time, the biofilm that forms in carbonaceous adsorbents can metabolically learn how to degrade some contaminants, not all contaminants, but some contaminants. And so sometimes if you just give time for the biofilm to acclimate to the presence of the pollutants, they'll slowly begin to biodegrade them. So we recommend that people compost the spent char. You could put it in your composting toilet, or basically keep it away from water sources. But for the most part, we don't expect this to be a very serious hazard, releasing chemical pollutants to the environment or exposing people.
Thank you. The following question is there a way to get the material in your rat tested to see if it is good for the use in the filter and the application?
Is there a way to get the material tested? There's certainly ways to do it, but these things can be kind of expensive. We test a lot of chars. In general, what we try to do is produce a series of engineering guidelines, basically, for how you make the char, how you process it, how you use it in the filter. And we see through time, you know, consistent operation of these systems. And so we generally say, if you follow the guidelines, then we have X degree of confidence that you're going to get consistent performance with what we've seen. There's certainly ways to test a char. People always want you to test their char and test their water and all this kind of stuff. And it can be done, but it's expensive and time consuming to do. So we try to be selective about what tests we do to get just the information we need to be able to come up with designs that'll function in a way that's consistent and predictable.
Mm-hmm. I'm going to read a comment from John. John says, I would like to share an experience regarding our work in household water treatment in Niger Delta region of Nigeria, where we used high-grade charcoal generated from fishermen's ovens, biochar, to facilitate biosand filter construction. They've backed their research with wider tests in a government-registered lab at Port Arthur. So, John, I suggest that maybe you contact Josh with your experience and share. I would be interested as well to know more about your project.
Sure, I can put my contact info back up.
Yeah. A question, I think we're going to take one more question from the audience, and then any other questions we'll try to answer by email so that we don't keep you too long. So the question from Simon is there a manual for the design of the Biochar oven available?
Yeah, you can find it on the Aqueous website, aqsolutions.org. It's pretty simple, just mostly photographs and a little bit of description, but yeah, you can find that on there.
Oh, I'm going to ask a last question from Christina, because I wanted to ask something very similar to Christina asked, before the biochar water treatment is set up, do you have the group test their water source for all chemicals contaminants, or do you assume contaminants based on the geology and surrounding environment? Yeah,
generally speaking, we use more survey methods to try to understand what chemicals might be getting into the water. So like, for example, if you're in a farming village in northern Thailand, we can survey farmers to find out what chemicals they're using. We can go to the shops where chemicals are sold and see what chemicals are being sold at the shops. You can look for discarded pesticide containers and see what chemicals are in those. So we've done a lot of that kind of survey work, you know, and just create lists of possible contaminants. And then you can narrow that list down and say, okay, let's look at some of these chemicals. What's their environmental half-life? Are they likely to be persistent in the environment, or do they react quickly? Are they more likely to be sorbed to soils, or are they more likely to be water soluble and get into the water? And then we can kind of, you know, look at the physical and chemical properties of the different agrochemicals that are used and try to come up with suspects that might be in the water. In terms of field testing for different trace chemicals, this is a really complex, challenging subject. The best methods for really quantifying different contaminants, really identifying and quantifying them, are laboratory methods that are very expensive and sophisticated, like mass spectrometry. We are building the capacity to do a lot of this, and a new research area for us is going to be non-target analysis of water sources. So we are getting water samples from all over the world from different chemical hotspots, whether they're industrial zones or agricultural areas, and we're screening these to try to find what chemicals are out there and what their concentrations are and that sort of thing. And that's a big kind of ongoing process. But your best bet, if you're constrained by time and money, is to take more of a survey approach and find out what chemicals are used in the region, and then look at those and see which ones are most likely to be a problem, a persistent problem in the water sources, rather than trying to take samples and measure everything. It's really like agrochemicals, for example, are applied seasonally, right? So depending on what time of the year you take the sample, you may or may not see a particular chemical that's in the water. You know, the frequency of rain events and other things like that can really affect concentrations and the presence or absence of different chemicals. So if you want to take a conservative approach, you sort of have to cast a wide net first in terms of what possibly might be there, and then start to winnow down that list based on what you think is most likely to be a problem in the water versus other components. I mean, I should mention too that people that work in rural areas and work handling these chemicals, we're probably all familiar with seeing people out in the fields using backpack sprayers with minimal or no protective equipment, just spraying crops. You know, probably the drinking water exposure of those folks to chemicals is probably much less than what they're getting just through their work and through their jobs. So it's another important thing to consider, our exposure pathways, whether it's through residues in food, whether it's coming into contact with soil that's been contaminated, whether it's drinking water, or whether it's occupational exposure. You know,
Right.
with this biochar treatment, we're really just focusing on drinking water, but there could be a lot of other important exposure pathways too.
Right. Well, thank you very much, Josh. That was
Sure.
a very interesting presentation. I know there are a few more questions, but we have to end up this session as we have another one starting in less than an hour. So I
Wow,
invite
okay.
everybody to just contact you, maybe if they had more questions, just send you an email. So
Sure.
thank you everybody for joining, and thank you again, Josh, for your presentation.
Cool.
Yeah.
All right. Well, thank you all very much. It was a pleasure.
Thanks. Goodbye.